got Laura Bercic from MSSL, who's going to be talking to us about sun wind electrons. So I'll hand over to you, Laura.
Thank you very much. Thank you for inviting me to give this talk as well. So today I'll be talking about the sunward electron deficit. So this is a new feature in Electron VDF that was discovered close to the sun. And it's actually a subject that I've been working on already during my PhD, and now I continue to work on it during my postdoc at MSSL. So in the beginning of the talk, I will introduce a bit like what is the sunward deficit and a bit what are its properties. And then I will focus on two physical mechanisms that we believe are responsible for its existence and for its disappearance. So let's start. So I will start with a short overview of the solar wind. So as you all know, solar wind is a weakly collisional plasma which is escaping the solar corona. It consists mostly of electrons and protons. And so as it expands into the heliosphere, it pulls with you the magnetic field from the sun. And since magnetic field, since the sun is turning, we get this Parker spiral shaped field in the heliosphere. And now here on the bottom, I just showed two plots of velocity and density of the solar wind at different regions around the sun. So we have during the solar minimum, so during the quiet period, we have this type of structure where we have high-speed solar wind above the poles, and then in the ecliptic plane, we have this slow-speed solar wind, which is a bit denser. And then during the solar maxima, we have all this confused picture where the fast and slow wind are very mixed. So I show this just to show you the variability of the solar wind and how it can change in time and space. So, but we'll be talking today more about the electrons in the solar wind. Here I show the electron velocity distribution function. So if we look first to the left, we have the distribution function at 80 solar radii. I represent it with cuts parallel and perpendicular to the magnetic field. So the blue one is parallel to the magnetic field, and the red dots are perpendicular to magnetic field. And you can see that this distribution consists out of different populations. So we can represent it with three populations. The first one is the core. So it's here at low energies, and it's well represented by Maxwellian distribution function. Then we have this high energy tail. It's at all pitch angles, which are represented by the halo population. And here I fit it with a kappa distribution function. And then only in the direction parallel to magnetic field, we have this population called the strahl. This is a beam-like population which streams away from the sun along the magnetic field. But so in the heliosphere, these electrons, they move under the effect of Lorentz and gravitational force, Coulomb collisions, and plasma instabilities. And so their distribution changes over different radial distances. So if we just look at what's happening closer to the sun, this is the plot here on the right. We see that, okay, the core has higher temperature. This is what we expect to see closer to the sun. But also the strahl is much more pronounced. If you compare it to the one over here, it's much stronger. And then there's this new feature, which I will be talking about today. And this is the sunward deficit, which I show here with an arrow. So when I say deficit, I mean deficit of electrons compared to the Maxwellian fit to the core. So you see that these blue dots, which represent the data, they go below the fit here in the sunward portion of the distribution function. And this is the feature that I will focus on today. So now let's have a look also at two-dimensional picture of this electron distribution function close to the sun. So all these plots, they show just same measurement, but I show it in different representations. So here on the left is just original. It's just the distribution function directly from the instrument. So we can see the core and the strahl here. But you can see that, for example, the strahl is much better seen in the next representation, where I scale all the energy beams between the values 0 and 1. So all the anisotropic features stand out, and this allows us to see the shape of the strahl. Then the next one is normalized distribution. So in this distribution, we just divide all the pitch angles with the values along the perpendicular direction, so along here. So all the values which are smaller than the value along the perpendicular directions are in blue, and the higher ones in red. So here we can see two features. We have, again, the strahl, and here in blue is this sunward deficit. The last one is just the distribution divided by the Maxwellian fit. And so where we see yellow colors, this means that the fit is working well. And where we see red and blue colors, it means that the fit is either below or above the measured data. So in this plot, we can see very well the shape of the sunward deficit, which is a bit, so it seems to be stronger along the magnetic field, but actually its structure, it goes all the way past the 90 degrees pitch angle and reaches almost towards the strahl. Okay, so now let's have a look at some properties of this sunward deficit. So these are the plots taken from the recent paper of Jasper Halikas. And so what he plots here, so sunward cutoff is basically the energy at which the cutoff is found in Parker Solar Probe data. And so what we see here is that this energy decreases with radial distance. It increases with the core density, and it decreases with the bulk speed of the wind. But I think the most important relation, which is also seen in all these other three plots, is this one in the right bottom corner, when we see that all the data basically corresponds well to this equation, so that the cutoff energy is 5 times the thermal energy. So this is parallel core electron temperature. So this energy seems to be closely related to the core temperature. Now I show this other plot, which actually show us where and under which condition the cutoff, not the cutoff, the deficit is found in the data. And so Jasper divides the data in 3 different subgroups. So in blue here, we have the data where the cutoff exists. In orange is the data where halo density is more than 1% of the core density. And then the green population represents where we have and the cutoff and the halo. And so what we see, for example, in these first 2 plots, so we have just occurrence here, and here it's fractional occurrence. But we see that basically this deficit is present almost all the time below 0.3 AU, and then after this, there's almost no deficit present in the data. The same goes for collisional age, shown here. So basically, if the collisional age of solar wind, the electrons, is small, then we see the deficit, and for high collisional ages, we don't see them. Then we can see that the deficit is present for low beta values, and for the cases which have higher anisotropy, or actually lower anisotropy, but for more anisotropic cases. We have seen now some typical properties of this deficit and where we can find it. And now let's look at some explanations for its existence. So we will start with exospheric models. Exospheric models are one of the first models of the solar wind. They are collisionless models. And in these models, all the solar wind is accelerated by the ambipolar electric field. Here I show schematics how this ambipolar mechanism works. So if we imagine that we have the same temperature of electrons and protons in the corona, and since electrons are much lighter, their thermal velocities will be much higher. And so basically this means that all electrons can escape the gravity of the sun, but all the protons are trapped by this gravitational force. And so because the plasma, the solar wind, needs to remain quasi-neutral, then this electric field is formed, and this electric field accelerates the protons away from the sun and decelerates the electrons. And so because of this electric field, we have this electric potential in the heliosphere, and this electric potential affects the distribution functions in the exospheric models. So in exospheric models, we can divide the electron distribution function with respect to the electric potential in the solar wind into 2 populations. all the electrons which are moving in the anti-sunward direction and have energy higher than electric potential energy. So this is this part. These are the escaping electrons, and they correspond to the strahl that I was talking before. And basically they can escape away from the sun. But all the electrons whose energy is smaller than this potential energy, they will advance up to some radial distance and then fall back ballistically towards the sun. And so when they fall back, they can only fall back with the same velocity as they had in the anti-sunward direction. So we don't expect to see any electrons with velocities higher than the electric potential energy in the sunward portion of the distribution function. So this feature that we see here is called the electron cutoff in exospheric models. And so basically, if we know this electron cutoff, we can directly relate it to the electric potential in the solar wind. So now if we look again at the observed distribution function by Parker Solar Probe, we see that we don't have this abrupt cutoff like what we see in these collisionless models, but we still think that what we see, this deficit, could be the remnant of this cutoff, just maybe smeared a little bit by collisions or some other effects. So this is an idea for the origin of the deficit. And now we tested it with the simulation VCOP, which also includes Coulomb collisions. And we try to see if we see the same thing, like if we see the deficit which corresponds to the spacecraft, to the electric potential in the solar wind. So just a quick overview about what is the kinetic simulation VCOP. So it simulates the solar wind, which consists of electrons and protons. It's 1D in space and 3D in velocity. And so in this simulation, electrons are accelerated by the ambipolar electric field and protons. So the solar wind is accelerated by the ambipolar electric field, and it has a gravitational force working in the opposite direction. There's also Coulomb collisions, which are present between the particles. Okay, and let's see what we get. So this is the result of our simulation. And if we look first to the right, we see the electric potential that we have in our simulation box. So our simulation box goes from 3 solar radii to 50 solar radii. And here I show the results of 3 simulations, but it's not important right now. So these colored lines, they present our solution for the electric potential. And we compare it to 2 different analytical solutions. So Meyer, Vernet, and Isoki. This is the exospheric collisionless solution. And you see that actually the evolution of the potential is quite different than when we include collisions as well. And this solution from Bercic is a solution of Gibbs kinetic equation where collisions are included, in fact. And these 2 solutions seem to match pretty well. So collisions are important for the evolution of this potential. And then what we did is we tried to use this value of electric potential to predict where in the distribution function we will have the deficit. And actually this worked out pretty well. So we see that this cutoff energy, it predicts well the actual cutoff in the distribution function that we see in the simulation. So this all worked very well. So we went on and we analyzed the Parker Solar Probe electron data. And so we wanted to measure this electron cutoff velocity, and then from it calculate the value of electric potential in the solar wind. These are the results that we obtained. So we have the radial distance on the x-axis. So we spend radial distances between 20 and 80 solar radii, and we show the potential on the y-axis. The potential decreases with radial distance. This is what was expected. And we fitted this data and we found the power law trend. The power that we found, the power index was 0.66, which compares very well to the one that we found in VCOP, which was 0.55. In terms of absolute value of this potential, I overplot the VCOP solution that we just saw before. So with this black line, which is not exactly what we observed in the solar wind data, but it's quite close. So I think that this seems to all work pretty well. So then we used this empirically obtained fit to calculate, to go even a step further and calculate, so what is the contribution of ambipolar acceleration to the solar wind? So from this curve, we can calculate the evolution of the electric potential energy in the solar wind. So this is this curve in blue. And then we compare it to the gravitational energy in black. If we now subtract these two curves, we obtain the total proton potential energy, which has this typical shape like in exospheric models. There's a peak at some point at some radial distance, which is called Rmax. And basically what it means is that all the protons which reach this radial distance will be able to escape, because from this point on, the force on protons is positive and they just get accelerated in the anti-sunward direction. So if we just integrate this curve now, we can obtain the velocity gained by the solar wind protons through this ambipolar electric field. And so in this plot, I show this proton velocity, which consists from two parts. One is the acceleration by this ambipolar electric field. And the second contribution is just bulk velocity that was estimated at Rmax. So this is a very simplified way of putting it, but I wanted just to have the very simple and crude estimation of what is the contribution of ambipolar fields to the solar wind acceleration. And so we see that we get velocities on the order of 200 or 250 kilometers per second, which is about a bit more than half of the solar wind velocity observed by Parker Solar Probe. So I think if the sunward deficit actually is the remnant of this exospheric cutoff, this would be a very good result. Okay, so until now it all worked pretty well. It seems like our theory is holding well, but there is one negative side, and this is the shape of the deficit that we observe in solar wind. So here I just compare the distribution function which was obtained by BCOB. So this is the one on the left, and on the right, the distribution function observed by Parker Solar Probe. And what we see actually, if you look at the shape of this deficit, here you can see that this shape is circular. So it goes all the way to 90 degrees and even further towards the strahl. While in BCOB simulation, the shape of the deficit is very much oriented with respect to parallel velocity. So it doesn't have this circular shape. Here it's not very clear. You can see some simulation noise as well, but I think, yeah, that the shape is quite different than what we observe in the solar wind. So this is another thing that we still have to investigate. Maybe, so there must be some other mechanisms changing the deficit, which are not included in the simulation. Okay, so this was the first part about the exospheric models, and now let's have a look at the second part. So these are the resonance wave particle interactions, which we believe also have influence on the shape and size of the sunward deficit. Okay, so we proposed Whistler instability, which is driven by the sunward deficit. So here I make a schematics of this instability. We can see the core electrons in blue, the strahl is in yellow. And then if we imagine that we have some Whistler waves which are propagating parallel to magnetic field in the direction of the strahl electrons, then the resonant electrons will lay on the opposite side, so close to the cyclotron velocity of this Whistler wave. And these resonant electrons can diffuse along the curves of equal energy in the waveframe of reference, which are shown here in pink. But the direction of this quasi-linear diffusion will depend on the phase space gradient. So electrons always move from the regions with higher phase space density to the regions with smaller phase space density. And so in this case, when we just have normal core and the strahl, the direction is to the left. And if if electrons move along this line in waveframe of reference, in the plasma frame, they will actually gain energy. So this means that they need to, we need an already existing wave to give energy to the electrons so they can diffuse this way. And now if we have a look at the example B, the only difference between the two is that here I also include some sunward deficit. And because of this deficit, this diffusion paths, they change direction. So now electrons are able to diffuse towards the right, which means that they will lose energy in plasma frame. So in this part, it means that electrons can give energy and they can drive the growth of quasi-parallel Whistler waves. So we wanted to test this, this prediction with observations. So we used the solar orbital observations. We used the electron measurements made by EIS instrument, which are in high cadence mode. So we get pitch angle distributions with the cadence of 8 Hertz. We also use magnetic field data, and we use radio and plasma waves instruments to learn about the plasma waves which were happening at the same time. And so let's have a look at what we see. So here I show the selected interval. It's about 2 minutes long. In the first panel, we can see the magnetic field. So in blue is the absolute value, and the two angles are in pink and yellow. And here you can see that magnetic field is not varying a lot during this period. But now if we have a look at these basic wave parameters from RPW instruments, we see that things are happening on the smaller scales. So if we look at normalized magnetic field power spectra, so normalized means just divided by the value along this interval. And so different lines, they show properties of different frequency bins. And so we see that there are enhanced magnetic field fluctuations in the frequency bin of 26 Hertz and 18 Hertz. And so we see similar thing in electric field power spectrum. We see that these fluctuations are polarized. So you see polarization is almost 1 here. And the wave ellipticity is also almost 1, which means that they're almost circular. And now the last panel tells us that the wave propagation is close to 0 for this period, which means that these are circularly polarized parallel propagating waves. We can investigate these waves even more in detail during this period, which is marked with SWF. For this period, we have waveform available. So we analyzed also the waveform of magnetic field and electric field for this period. So we see this typical bump in the magnetic field spectra. And if we filter it, we see that these fluctuations are very circular. If we compare the electric and magnetic field fluctuations, we can determine the direction of these Whistler waves and the phase speed as well. So we end up with all the information needed about these waves to calculate what would be the resonant velocities in the electron distribution function. So where would the resonant electrons lie? Okay, so now let's have a look at the electron distribution functions during this period. Here is just an example of how the distribution function looked like at this during this time. So we see we have the core distribution, we have the halo distribution, and we have the strahl, which is more or less weak because this is happening at the 0.5 astronomical unit, more or less. We see that so here we have pitch angle distributions for different energies, and at small energies, we kind of have 2 peaks, which kind of shows the anisotropy of the distribution. And then at higher energies, we just have 1 peak, which represents the strahl electrons. And since there's quite some noise still in this data, we use time averaging to have better signal to noise ratio. And so we make these time averages for, we create distribution functions for these periods A, B, C, and D. So yeah, these are the distribution functions for this time periods. The periods B and C, and you can look at here again. So B and C, they correspond to the time where we had this Whistler waves present, and A and D is just before and after. Then, okay, so we see in these distributions that we have the strahl electrons here in red, and we see that there's also this deficit present here in blue. We now use the parameters derived for the waves And we just overplot it in this plot. So we have the phase speed of the wave and the cyclotron velocity here. And we see that the cyclotron velocity corresponds well to the location of the sunward deficit. So we think that the deficit and the waves must be connected. Also, we can see that this deficit is more pronounced for the examples B and C, which happen during, which coincide with the wave presence. So now the question is, which of the two scenarios is happening? So are the electrons giving energy to the waves, or are the waves giving energy to electrons? So what we do is calculate the pitch angle gradient of this distribution function in the waveframe of reference. This is what is shown on this plot here. In red, we have positive pitch angle gradient, and in blue, negative pitch angle gradient. And we see that around this cyclotron velocity, the gradient is negative, which means that the quasi-linear diffusion can happen in the direction to the right. Now, this corresponds to this example B, when the deficit is present. And so in this case, the electrons, when they diffuse this way, they give energy to the waves, and they can drive the growth of these Whistler waves. Okay, so there was another publication by Kuzic et al., which I'm showing here, where I think that the other scenario took place. So so they do a particle in cell simulation of the Whistler heat flux instability, and basically they start with the electron distribution function with drifting core and halo, so just to trigger the Whistler heat flux instability. Then they observe these quasi-parallel Whistler waves, and then these Whistler waves, they interact again with the electrons. So if we just look at this plot C, this is the comparison between the initial and final distribution function. So we have waves which are propagating in the positive direction here. So the resonant electrons are in the negative velocities here. And what they observe is that electrons moved from the red region here to the blue region here. So basically, it means that they followed this diffusion path. And now with this A and B examples, we have two different things. So either in the example B, electrons are filling this deficit, so they're destroying the deficit. But in example A, they are creating the deficit. So it would go both ways. Okay, so this brings us to the end of my talk. So what I try to show you today is what is the sunward deficit and what are its properties. And I try to discuss which physical mechanisms could lead to, could be responsible for its creation and disappearance. So we saw that this deficit could be a consequence of the exospheric cutoff, like something that comes from exospheric models. But there is one thing that doesn't go with, so this is the shape of the deficit. And then another possibility is that this deficit is responsible for, or is taking, could be created and destroyed by different resonant wave particle interactions. But I think that future work is needed to make really good conclusions on what's really happening and why. Okay, so that's all I had to say.
Brilliant, thanks, Lyra. So if you have any questions for Lyra, oh, hang on, first I should probably press the applause. There we go. I think we can do virtual applause.
Thank you.
As I see a few other people are doing. If you have any questions for Lyra, feel free to unmute yourself or raise your hand and we'll try and get to you. But maybe while people are thinking of questions or forming them, the wording in their head, maybe I can start, if that's all right. So I just wondered, electron observations or measurements are kind of notoriously difficult to make because of spacecraft potential.
Yeah.
How sensitive are the distributions you're getting from probe when you've got non-spinning spacecraft that's in some pretty intense sunlight?
So I think with the closer you go to the sun, the spacecraft potential decreases. At least this is what we believe for now. I don't know if some strange effects will take place, but I think that for now, the problems with spacecraft potential are bigger further from the sun, so at 1 AU, than when you go closer. Oh, right. So really on these distances that I was showing, they estimated that the potential should be on the order of like 1-2 volts, maybe 5, but compared to the size of the distribution function and the energies that we're observing, I think it's not very problematic, but yeah.
Okay, well, sounds great then. I had no idea that it dropped with distance.
Yeah, so it has to do with the plasma parameters, and they change in a way to decrease the potential.
Other questions for Laura? Well, I'll monopolize things and ask another then, if that's all right. So you could clearly see in the distributions you showed how the strahl was getting weaker with distance, presumably because the magnetic field is getting weaker.
Wait, so let me just find the distribution back. Yeah, I think that there's a whole question about what's happening to the strahl during the radial extension. So what the observations show that actually the strahl is much more narrow and prominent close to the sun, but then as we move away from the sun, it's getting scattered and maybe moving, like scattering all the way to become isotropic and then to actually be a part of the halo population. But this scattering is still a big question, because so we have different scattering mechanisms which are possible, like collisions, wave particle interactions, or interaction with turbulence. But I think this discussion is not completed because so we have the scattering by the waves, but we don't observe waves all the time. So yeah, I think it's still a part of discussion. So why the strahl is becoming weaker.
Okay.
But for sure, it also has to do with, so the focusing effect, it depends on the radial gradient of the magnetic field in the solar wind. And so as because of the Parker spiral, the radial decrease in magnetic field is, it starts to be slower. And so the focusing mechanism, which is actually forming the strahl, is also weaker.
So if I could ask you to speculate for a second, then, do you think probe will get in close enough to see the strahl starting to form? Because this is sort of evolution of the strahl after it's formed. Will the probe get in close enough to see the formation of the strahl?
That's a difficult question. I guess, yeah, I don't think the formation of the strahl would be at one exact radial distance. It's a very gradual process in my mind. So I think we're already seeing quite different properties than what we've seen so far. Like every time that we go to closer radial distances, the strahl is more narrow and maybe has more Maxwellian shape. So I don't know, yeah. No, I think, so if now we are at 16 solar radii, and if it goes all the way down to 10, this is like another third of radial distance. We could see some interesting stuff happening to the strahl, I believe.
Yeah, indeed, interesting times. Okay, thanks very much, Lara. Does anyone else have a final question? If not, Chris, you've unmuted. Were you going to?
Well, I was just going to, in relation to that conversation you were just having. Morning, Laura. Morning, Matt.
Hi.
So I think it's a nice demonstration that you explained that the deficit either either creates the Whistler waves or the Whistler waves fill in the deficit. But then in the past, those kind of waves have been proposed as ways of broadening the strahl. So is there kind of a bootstrap mechanism where the deficit creates the Whistler waves that broadens the strahl, or are those processes just happening in too far apart in phase space for those to be related? I mean, I don't know whether that's a sensible question or not, but it's sort of, you know, is there a relationship there between all of these things?
I don't see it exactly between this type of Whistler waves and the strahl, because so these are the anti-sunward Whistler waves parallel to magnetic field, and I don't think they can scatter the strahl. But if you would have sunward Whistler waves, which are parallel to magnetic field, right, they could scatter the strahl, and the oblique instability as well. So the oblique Whistler waves, they appear to scatter the strahl very efficiently.
Right, so they are happening in different halves of your phase space, so they can't.
Yeah.
They can't be related. Okay.
Maybe they can be related in a bigger sense, like first one instability is triggered and then it triggers the other instability, like a chain process. But I think that these particular waves, they could not interact with the strahl.
Okay.
Okay, great. Thanks, Lyra. If there are no other questions, then I'll wrap up the meeting. So see you all in a month's time. Beatrice, do you know who the next speaker is? I haven't looked at the schedule.
Oh, I didn't actually. I looked at before the meeting, but now it's, yeah, I will need to have a look. But we will send an email with all the information. So yeah.
And we'll upload this talk to YouTube later today, if that's okay with you, Lyra.
Thank you.
Brilliant. Okay. See you all soon.
Bye-bye.
Bye. Thanks.